Alrighty, let's get this show on the road. Alright, so I figured I would, I know it's Friday, but I figured I would get started. This is actually a makeup of a presentation I was trying to do yesterday, but there was enough technical issues where I needed to delete the stream and kind of start over again. So one of the things I figured that we could do is maybe take it in a little bit of a smaller chunk today. So instead of, I don't think we'll go a full hour. Depends on the interaction that we get. But I think this will be good. We've got so we got a foundation. If you saw a previous video that I have created in week 1, we went over what GIS was, some of the tools we could use, like QGIS, what you see here on the screen. And GIS is super powerful. It's used in nearly every single industry. And what I figured we could do is I figured I could teach you all how to use GIS and remote sensing tools for emergency preparedness. There's so much you can do with it. I figured what we would do is we would have a series where we would step from very, very basic all the way up to some advanced tools and methods, and use it so we could better understand the world around us. You know, may not realize that there's, this industrial plant just a quarter miles away that could potentially, threaten your home or something. Or if an event does happen, being able to use GIS to make tools to make your own map so you can get out of Dodge. That way you're not dependent on the grid. Even if you have Waze, everybody else has Waze, and so if you need to figure out a way to get out of town, why not utilize a map or a map book atlas that you create on your own so you can figure out how to get out of town. Also figure out, where water sources are, where some, potentially natural resources are. I mean, there's so many different things we can do. And I figured that this could be a pretty dynamic series. So, yeah. All right, so week 1, we put our first dot on the map. If you remember, I chose the home from Groundhog Day, Bill Murray. But you feel free to use your own. Just as a quick refresher, we installed a plugin that allowed us to geocode our own address. So if you need a quick refresher, that plugin, you go to Plugins, Manage, and then we can see my installed plugin. So there were 2 plugins we dealt with last week. 2 plugins. What the heck's going on? The first one we installed was geocoding, and then the second one we installed was Quick Map Service. Geocoding is the one where you type in your address and it'll put it on the map for you. What it does is it takes your address and puts it into lat long. The Quick Map Service one, that allows us to have a series of base maps. So base maps, again, are the pretty wallpaper that you have on the background. It's a static picture. Pictures are rasters, remember? So you can't interact with it. It's usually just used as a background, pretty background. And so Quick Map Service is a whole list of base maps that we can use. This week, I did preload this project with some data from the U.S. Census. Believe it or not, the Census Bureau has fantastic data, especially geo-enabled GIS data. All you have to do, you can do a simple Google search for Census GIS data, and it should come up. But specifically what you're looking for is the tiger line shapefiles. If you're looking for tiger line, the last year that they published for tiger line files was 2020, even though the 2020 census came out. There is a newer set of data. Instead of shapefiles, there is a file type known as a geodatabase. Geodatabases they used to be a proprietary format under Esri, that's ESRI. They're one of the biggest players in GIS mapping software. But geodatabases allow you to store multiple features. Shapefiles are specifically geared towards one type of data, whether it be roads or rivers, or any shapefiles are vector files. So remember, rasters are pictures, vectors are linear attributes, linear or polygon or point features, and they have a series of attributes underneath them. So for us, I felt that downloading the geodatabases were probably better since we're dealing with a national level. Geodatabases allow you to also compress a bunch of features into one single package. Depending on your computer resources that you have, this might be a bit big. You can see that the address range geodatabase is almost half a gig. Census blocks are a little over almost 3 gig. So depending, again, your computer just has to have enough resources to read it. So if you can handle data at the national level, that's great. But you don't have to. You can download these individual Tiger files, and you can choose all of those different subsets, whether it be the census block, census group, census tracts, place names, school districts, zip codes, all line files, which all line files include coastline, landmarks, road, rail, military installations, water, and then relationship files. Relationship files are tables that you join to features to get more insight, and we'll do that later in the series, but we don't have to do that now. The first thing I want to do is demonstrate to you how to create buffers, which are essentially range rings around a central point, which will be our address. And then, depending on how it goes, and hopefully my computer won't crash out on me this week or tonight like it did last night, we can build service areas. So instead of generating single circular buffers, we actually create distance rings based upon a road network. This is really great. We call this service areas. And so if, like a business use case might be, I have this warehouse and this warehouse and this warehouse, what are the service areas? How far can a driver travel within a day? And so I can essentially network all of those together to see if I have any gaps. Good example, this actually might be really good to do for your own use cases. If you have fire stations and police stations, how long, in theory, would it take for a police station, a police or fire asset, to get from the station to your house? It might be longer than you think. So same thing about getting out of Dodge, right? How far can I travel in this given amount of time? So yeah, let's jump back into QGIS and do it. Alrighty, so one of the things when it gets to projections are very important. And again, going back to what we talked about last week, if you choose the wrong projection for your data, you're gonna get bad data out. Bad data in, bad data out. QGIS isn't necessarily as forgiving as maybe some other tools out there, where it'll try to do some stuff on the fly, reprojecting. We call reprojecting on the fly, but best practice is to make sure everything is in the same projection, and that projection is geared towards whatever it is you're trying to achieve. Ideally, you're choosing a projection that's in your local area, your area of focus. If it's a continental level mapping, you're going to choose a projection that best displays that data at a continental scale. For me, for this project, again, you can choose your projection based upon what it is you're trying to achieve. But for me, we're focusing around UTM Zone 16. So this band in red here is the UTM Zone 16. So anything within this UTM zone is a good way to map with UTM Zone 16. If we choose 15, you can see it's the next one over. 17, same thing. 18, it just steps over. We choose this because this allows for the least amount of distortion. Again, the world is round, and we're projecting it onto a flat surface, so we're introducing error and we're introducing distortion. So we're going to choose NAT83 UTM Zone 16. That's the ESPG code. Pretty simple. Just give it a second to re-render. Okay, so we have our project in UTM Zone 16. Let's just double check our data to make sure our data is sitting in UTM Zone 16 as well. Again, it is. When you right-click the layer properties, go to Source, and your Assigned Coordinate Reference System, CRS, will display here in this window. Cancel out of that. That's important to know because when we go into our geoprocessing tools and create a vector buffer, it will pull in the type of, if it's projected to like UTM zones. UTM zones are measured in meters. It can also do the conversions for feet and imperial units. If we were using WGS 84, which is a geographic coordinate system, a geographic coordinate system is more like lat long. If you're familiar with that, it's unprojected. It's in geographic space, and that's where you get latitudes of a sphere and longitudes of a sphere. But for us, we need to actually project in order to do measurements and distance calculations and area calculations. For our all intents and purposes, we need to project it. So let's get started here. So we've got our input layer, which is our home. I'll load that in. Our distance, let's just get started with 400 meters. Right? Immediately right near our house. So we'll do 400 meters segments. This allows you to kind of show how rough of a buffer each segment. So a polygon is drawn, and the more segments you have, the smoother that polygon will look. So if we get 5 segments, what we'll do is we'll change this to, I don't know, we'll change this to maybe 50 segments. Doesn't really matter too much. End style, round, flat, square. So we're gonna make a round buffer around this point, and that's it. We'll just put it into temporary space for now. I'll just take a look. All right, it ran. All right, now we're super zoomed out. So we actually, this dot is covering up. It's covering up our buffer at 300 meters. So if we zoom in, we can see that there is our 400 meter buffer. And if we take our measurement tool, choose Cartesian, and we take the center of this point and drag out, you'll see that we're at 400 meters. So we know that we did it right, and we know the area worked. Now let's just see what is in. So in this 400 meter buffer. So let's change this style. Let's just make this a big red outline. Apply. Okay. Now you'll see it's just plain old tan. That's because our base map right now is just this USA administrative file. It's just the plain states on a white background. There's no real context here. We'll build up to that, to building our own base map, but for now we're going to borrow our base maps from OpenStreetMap, OSM. So we'll turn off this layer, and then let's turn on OSM standard. All right, now we've got some context. All right, so we can see that our home is sitting on Fremont Street. We can see that there's a parking lot. This doesn't, well, it's good. It doesn't give us full context. Let's look at some imagery. So we can go into open, we'll open our quick service, what is it called? Quick plugins, let's look. Quick map services. All right, so we can open up our quick map services button, and let's choose Google. Let's choose the Google satellite. Now when we added that layer to our table of contents, this layers here, you'll see that the Google satellite jumped underneath. All we have to do is turn that off, and there we go. So now we got our imagery, and we can see that this is a pretty good neighborhood. So here's a buffer. It's one single buffer at 400 meters. What if we want to do more than that? Maybe we want to do a buffer every 1 kilometer. There's another tool. So instead of going up to vector geoprocessing tools buffer, there is a processing toolbox tool called Ring. I think it's called Rings. multi-ring buffer, constant distance. So if we double click this, up pops another tool window, and we can do a multi-ring buffer with a constant distance around any input layer. We could do home again. So maybe we want to make 15 rings, each 1 kilometer out. Or maybe we want to do 4 rings at 400 meters out. It's about a mile, I think. No. Yeah. 4 laps around a track is a mile. So that's 400. Yeah. Alrighty. So let's try that. So we'll do number of rings 4. And then we'll do 400 being the distance between them. And we'll also make this a temporary layer. Temporary layers may or may not get saved in the project. Chances are, if it's a temporary layer, what will happen is when you close the project, close your computer, that will be gone. It's just stored in memory, and it will be gone. If there's something, it's good for, just kind of testing something, and instead of writing to disk. Not that big of a deal, but for me, when I'm just kind of testing things out, I just store them to a temporary layer. So we'll run this. There we go. Close. So now we have 4 rings. If we open up the attribute table, you'll see that we have 4 concentric rings, each 1 distance apart. And you'll see each ring is a, so you've got your first central ring, this 400 distance, ring ID 1 contains a closed polygon. This is a ring around this. So if you wanted to search for items in between these two, you'd have to select both of them. If you wanted to select features that are within 800, within the 400 to 800 range, that would be this ring. 800 to 1200, and then 1200 to 1600. We can change the styling for this also. So maybe we want to do different styles based upon, so we can do a single style. So we can do single. Let's get rid of that selection. So we have a single style, all of them being red. Red's not great against imagery. Yellow is actually usually better. Or what we can do is we can change the style if we want to be categorized. So then what we could do is we get to categorize it based upon any attribute in our attribute table. So let's categorize this off of ring ID, and we'll do random colors. Sure. And this should work. Fill. Blue fill. And apply. Okay. That didn't work. Styles can be true. Oh. When you add them, the reason why nothing showed up is because I didn't classify any of them. So you have to classify, it adds all of the attributes to the symbol map, symbol table. You hit apply, there we go. And now you can see, now we've got each different range ring. So that will show us, it's just one way to visualize it. We can change the transparency if we want to. That would be rendering, I think. Display. There's a couple of places where this goes. Where'd it go? Layer rendering. Opacity. They always hide it. Each version of QGIS that comes out, I feel like they keep changing and putting things. So if you want to make this a little transparent, you go to layer rendering, turn that down, and then you can see, if I don't keep changing that window, you can see we made it a little transparent. This is, while it doesn't seem very important now, you'll see once we start building our own maps that this actually being able to style and change things and see how things are rendered actually do become pretty important. All right, so we've got two different type of rings here. We'll put this back to what it was. And you can see here in the layers table, if we want to, we can actually turn off these individual attributes, which is pretty cool. Turn that off. There's our original buffer, 400 meters, and then there's our bigger range ring. But there's another way, which actually is way more cooler. And this is called, it's part of a network analysis. So roads are networks, and doing network analysis allows us to create those service areas. So what you do is you point it to a road network and say, go get me, or draw a buffer, a ring, as close to a ring as possible, X distance away from my point, or X time away. So if we're dealing with speed, if more advanced road networks in some GIS tools have attributes that talk about like direction, whether it's a one-way road or two-way road. They have the speed limit on there. Your Google Maps, your Waze, your Apple Maps, all of that type of routing is all based upon those advanced features. That's why Waze generally, and Google hopefully, and Apple, all of those, they will try to use the most up-to-date data, or if it's a new road, or if it's a road that changed to a one-way or whatever. It's not perfect, because generally they're all pulling from the same data source, believe it or not. But they try. So we're going to do something similar. Now, the challenge that I'm going to have tonight is, this is a big file. This is every road within the U.S. according to the U.S. Census. So I'm going to clip this first. I think what I'm going to do is I'm going to try to be smart. Emphasis on try. So we're going to do some geospatial analysis here. I'm going to turn off these roads because I don't care if they draw. But I'm going to take the surrounding states of my point, and I'm going to use my selection tool, and I'm going to select these surrounding states. Sure. I have to select the states first. So you select the states within the attribute table and in the data layers. You draw your box. That will select them. If you want to deselect, you hit Control, and that will get rid of one. But how far is? What I want to do is I want to select. All right, this is 5,000 meters, 2 miles. 300, yeah, all right, 300, 400, all right, we're gonna do this. Just out of reach, okay. I'm actually going to select those. as well. So now what I do is there's a 1,000 different ways to skin this cat. For me, what I like to do is, now that I have this selection, I like to right click the layer, and then I like to save selected features as, and what this will do is this will make a new vector file, depending on the format that you choose, for that selection. If you don't have to make a new file. You can do everything in memory, and you can do things off of the attribute table and the selection within itself. But me personally, I kind of like to do a new file. It keeps things a little less computational intensive, in my opinion. I'm sure there are some that will disagree with me, but that's just me. I also, in the process of creating this new file, I get to choose the project projection, which allows me to reproject as I'm exporting, which is super awesome and super easy. So we're going to name this file, and we're going to call this states of interest. It'll be a spatial light database. Fine for now. And all those other features are good. It wants to reproject. It's asking us, hey, the projection that you were in is not the same as you are going to, and there has to be some math involved in order to do this. So what formula and what process do you want me to use to do this? I'm going to choose this North American number 16. It's the one that seems to have given me the least amount of problems in doing this before. So we hit OK, and there we go. We got our new map. All right, so now that I have these features, what I'm going to do is I'm going to use these to clip out these roads. So what we'll do next is we will go to Vector, Geoprocessing, Clip. Our input layer is the layer that we want to clip. So that will be US roads. Our overlay layer is the states of interest. And let's write those out to, and we'll save those to a file as well. And then we'll rename that one. Save. Yes, we want to replace it. And we'll open that file. Hopefully this won't take too long, but we'll try. I'll see what happens. It may take a bit. All right, so while that is running, do you in the chat, in the room, have any questions? Nope, no questions. Now we'll let this run. Hopefully this won't take too long. Now it should be good. 11%. That's good. And obviously the faster the computer you have, the more powerful the CPU, the more memory you have, the better these types of geospatial analysis will perform as a whole. What I've found is that over the years, the more powerful the machine, the more I get lazy and add more stuff to the map without thinking about it, it's the same thing like with your Google Chrome and Firefox tabs, I'm sure. You just keep opening more tabs and more tabs and more tabs and more tabs, and before you know it, you get 100 tabs open and your computer's running dog slow. Same thing in GIS land. And if you're interested in getting into GIS, this is pretty much what you do a lot of the times, and is waiting for things to run. And as computers get more powerful, those wait times come down, but we start doing more computational intensive processes, so we start pushing it to the max again. So. But if this works, this will be, I'll be pretty excited, because I do really want to show you these service areas. I think it's pretty nifty. So Patches, if you're still watching, where are you from? All right, I did it. We can close this. Close all these warnings. We don't need to know these warnings anymore. All right. Where did it go? Layer has no coordinate reference system set. This layer is not georeferenced and has no geographic location. That's odd. Well, let's set one. Invalid projection. Well, we know our input layers were UTM zone 16. Let's try that. Of course. Okay, well the data is there. That's good. The problem is it's in the wrong projection. We're in no man's land. I don't even know. Yeah. We're in no man's land. Kind of, actually. You can see this really is not in the right spot. So we chose the wrong projection. So there's only really 2 projections we've ever dealt with in this project. So let's try to put and see if we can set it to the other one. And then, you know, this might have been a bug. To double check, let's use the projection. We'll set the properties based upon this one. So this was Esri 10/20/09. So if we set this one to 10/20/09, I bet you it'll get put in the right spot. There we go. Yep. Okay. That's okay. What we will do then is, before we get anywhere too far, we will reproject that layer and actually define it into what it's supposed to be. So let's go and set it to UTM zone 16. And let's run it as all right. Yeah. So what happened is for whatever reason, when we clipped, even though it lined up in the project, the roads lined up to where they're supposed to be in the project, when we clipped, the clipping operation didn't preserve the road. Oh, it actually didn't preserve the projection, because you saw when it came in it was unprojected. However, the underlying data was still projected in the original data source, not into the desired clipped projection. So what we had to do is we had to go in and set the projection to be the original projection that the original file was in. And then now what we're doing is we're reprojecting that into a new file into our UTM zone 16. I think instead of IPOE, this project's going to be understanding projections and how they work in QGIS. So we'll let this finish. What time is it? 9, a little after 9:20. How long have we been going? Okay, almost 40 minutes. All right. Alrighty, that finished. Let's close. There we go. There's our reprojected layer. Look how awesome that is. That's great. Alright, we need to save it though. Save features as spatial light database. The reason why I'm choosing spatial light is it is a file-based database, and the power that this has is when you have a lot of features, you can do something called indexing, which is an operation where it speeds up the process of understanding where, when you query the file and says, I'm looking at this area, it knows the features that it needs to return to you, instead of saying, hey, which features are already there. We've already done that indexing operation ahead of time when we write the file. That's why it takes a little bit longer to write them. However, it speeds up the process when you are trying to render and process data. So we'll call this AOI roads UTM. Let's change the Z16, and I'll just change this to be all caps or something. I'll go in and delete these other files. Save. And it's just going to rewrite that file, and we'll clean up our project here. It's pretty crazy how many roads we have in the US. See them all trying to draw. It's just so cool. Now it's 99%. It's kind of sitting here for a little bit. think it's running the indexing process now that all the files, all of the features have been written to that file. Hopefully the computer won't crash. Just save it real quick. And it's done. All right, so get rid of this reprojected, remove this entry yes, turn that layer off, don't need this layer either, turn that layer off, don't need, yeah, we still have this little buffer, yeah, good. All right, and there is the roads. All right, now instead of doing a circular buffer, let's create a service area from layer. Now that we have our, all right, so now we need to vector layer representing network. Let's choose our vector network that we just created. Travel cost. So again, we don't have anything in our attributes that represent, we don't have anything, I'll just show you. We don't have anything in here that represents speed. I'm almost positive. Oh, this is going to take a second now. There's a lot of features. Shouldn't have clicked it. Even though we indexed it, it's still, QGIS still has to go through and read every single feature inside of the table, and then it'll represent the table. You can see we're at 1 million features, 1.2 million, 1.3 million, 1.5, 6, 7. There's a lot of features in here. I think I'll just, well, I want to show it to you. This can be a little finicky, so I'm just going to let it do its thing. This is kind of where I ran into problems last night, although I ran into it when I did it for the whole US. So let's just give it a second here. Because my computer will hang. Hopefully you all are still on the stream. I didn't get bumped. What's happening is it's now storing all of those features into memory. Really shouldn't have clicked on it. Just give it some time, because I don't want this project to crash. Okay, so it's here. Let me just see if I can pull it up. All right. Long time, but it was worth it. So here are all the attributes that relate to every single record. This is 3.6 million features. Because this came from Census, you can look up all of these attributes and they will tell you everything that means. So here's the ID of that road, the full name of that road, the road type. I don't know what MTFCC means. If there's a prequel or a pre-directory, pre-direction type, surface type. These are all related to, is it dirt road, is it a paved road? they're all things that will allow us. So if we wanted to say, hey, only show me paved roads, or show me primary and secondary roads, I'm sure those are certain types in here. They just represent a code, and we could look that up later. But as you can see, there's nothing in here that talks about direction or speed. Only distance, and distance is something that's measured off of a feature that you don't see in here. It's called the geometry field, and that actually tells you what the computer to render. So we'll go back to service areas. We'll just do them really quick. AOI from roads, UTM zone 16, shortest path. We're going to start from our vector, and then we'll do a 400 meters. It doesn't tell you what this distance is because it assumes you know that it comes from the projection of your, I'm not sure if it's your project or if it's the road network layer. It's probably the road network layer. This is where, again, projections are really important. Make sure that your roads are projected in a format that will allow you to measure travel cost, distance, in our case, appropriately. And we can stick with the defaults. We'll let it run. And hopefully this won't take too long. I have a feeling it might, though. All right, maybe this, I'll let this run, and maybe we'll catch up next week. I think there was enough in here for this week's kind of live training. I'll let this run. We'll see how it goes. We'll pick it up next week on taking these service areas and running it to the next level. We'll show what they look like. All right, everybody. Again, if you need any help in emergency preparedness, doing any of this GIS stuff, you want to do it on your own, but you're not sure where to get started, please reach out to me. Best email. Email is the best to reach me at. Hit me up at team@threatowl.llc. You can catch me on the Grayman Network if you want to. Visit our website, threatowl.llc.com. No, man. threatowl.llc. No .com. threatowl.llc. All right, everybody. Stay safe. Have a great weekend, and I will catch you all later.